Hi, this is Jeff Spence, your Math 135 instructor at Community College of Denver. We're going to start doing 5.2, which is the second section of probability. It's titled Combining Events. Kind of a misleading title. The main thing I want you to know in 5.2 is we're going to be doing probabilities of events when we conduct one trial of an experiment, or like one selection. If we select marbles from a bag or something, we're talking about one selection. So keep that in mind. The next section, 5.3, will be where we'll be doing multiple selections. So first in 5.2, we could talk about the complement rule. I'm going to go over that quickly. It's pretty straightforward. The formula in your formula sheet and in the book says, in orange, the probability of A superscript C, which means A complement, equals 1 minus the probability of A. Well, that's because the sum of all the probabilities adds to 1, so it's like the yin and the yang. If you add the yin and the yang, that's this and that. If you add it all up, it needs to equal 1. So if we look at an example, these examples here, the probability of, I haven't told you what the experiment is, but I'll tell you now. For the first one, it's rolling a die, and we want to know the probability of not rolling a 6. Well, that's pretty simple. Not rolling a 6 is everything but a 6. So all we have to do is 1 minus the probability of rolling a 6, and that's 1 minus 1/6, which is 5/6. Next, if we select a card from a deck, a 52 card standard deck, what's the probability that we don't get a king? Now this could happen sometimes when you're playing poker, you don't want to see a king. What's the probability that we don't get a king? Well, 1 minus, and what's the probability that you do select a king? There's 4 kings out of a 52 card deck, and that would be 48 out of 52, which we could reduce to, let's see here, we can do 24 out of 26, I can reduce again 12 out of 13. Or you can give it as a decimal, it doesn't matter. Okay, and then lastly, the probability of at least one something. Now, I haven't given you an experiment or anything like that, but remember, if you want to do the probability of at least one, that means, I'm going to write up here on the upper right-hand corner, at least one means the number 1, 2, 3, 4, 5, and so on, up to n, depending on how many trials you run. So at least one means everything but 0. Let's say we were talking about the number of people waiting in line. There could be 0 people waiting in line. So we have to get rid of everything but 0. We want everything but 0. So we do 1 minus the probability of 0 people waiting in line, and then we can get that answer. The only thing is I don't have an experiment where we can figure out what the probability of 0 is. So I'm just showing that this at least one thing is going to be a fairly common thing we're going to see. Next up is the addition rule. We're going to spend a little bit more time on this, 2 slides. So the addition rule you'll have in your formula sheet here in black. It says the probability of A union B, or in other words, or. The union sign in the middle means or. So the probability of A or B equals the probability of A individually plus the probability of B individually minus the probability of A intersect B. In other words, the probability of A and B happening at the same time. Let me make that note. This last part is A and B at same time, or on the same selection. Okay, so let me start off with some examples that are mutually exclusive, and I'll kind of explain mutually exclusive at the end. So let's see here. So the first example is if we roll a die, what's the probability that we roll a 2 or a 6? Well, what's the probability that you roll a 2? It's 1 out of 6. And then the probability, so that's the first event, the probability of A. And then the probability that you roll a 6 is 1 out of 6 as well. Okay, so I've taken the 2 events separately. And then if I roll one die and I want to know the probability of getting a 2 and a 6 at the same time, that's this part of the formula right here. Is that possible? Can I roll a 2 and a 6 at the same time? No, I can't. So this probability is 0. So we just take the 2 probabilities, add them together, 2/6, which reduces to 1/3. Okay, next, imagine if we flip two coins. The book did this sample space. Probability that you flip two coins, and or sorry, not the probability that you get a head or a tail. From the book in 5.1, we saw that the probability of getting a head or a head and then a head was 1/4. The probability of getting a tail and then a tail was also 1/4. But can we get a head and a tail and a tail from the same two flips? No, we can't. It's impossible to get a head and a tail in the same two flips. So the probability of that is 0. I hope you're noticing a theme here. That's 2/4, which is 1/2. Let's skip down to the king or queen. What's the probability if you select a card from a 52 card deck that you get a king or a queen? Well, the chance of getting a king is 4 out of 52. The chance of getting a queen is also 4 out of 52. But from that one selection of a card, can we get a king and a queen on the same selection? No. So the probability of that happening at the same time, the and part, is 0. And we get 8 out of 52, which is, you can reduce to 4 out of 26, which can be reduced to 2 out of 13. You can give that answer as a decimal. Now notice, all these events, I'm skipping this red and black one, all these events, 2 or 6, head or tail, king or queen, they're all mutually exclusive because they can't happen at the same time. They cannot happen at the same time. So therefore, the probability of both of those events, A and B, in all cases is 0. Notice it's 0 for all three of them. So that's what it means to be mutually exclusive. Can they happen at the same time? If they can't happen at the same time, they're called mutually exclusive. To finish up 5.2, we're going to look at the addition rule from tables. Using the addition rule, doing probabilities from tables. I rewrote the addition rule. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Let me remind one more time, this is really important for 5.2, that we're only going to be doing these probabilities from a single trial, meaning one selection. Keep that in mind. The wording will, lead you to understand that we're only running one single trial or one single selection. So I have this table here I just made up where we're talking about basically hair color and whether you're male or female. So I put together male and female on the left, brown, blonde, other on the top, and the totals on the outside. Okay, so for instance, there's 8 males with brown hair, 6 females with blonde hair. There's a total of 30 females, a total of 20 males, a total of 50 people. So all these examples, we're going to select make one random selection. Now imagine all these people are in a classroom, and I'm just going to close my eyes and select one person. That's the experiment for all of these. So if I close my eyes and all these students are in a room, what's the probability that I select a male? Well, if we look, there's 20 males out of 50 people. So 20 out of 50 reduces to 2 out of 5. Okay, next, if I close my eyes, out of all 50 of these students, what's the probability that I select somebody with brown hair? Well, it looks like there's a total of 14 people. If you go down the brown column, there's a total of 14 people with brown hair, and out of 50. So 14 out of 50 will reduce to 7 out of 25. Okay, so both of those examples, those first two, are really from 5.1. They're just simple probability questions. What's the number of ways it can happen out of the total? Next, the probability of male and blonde. So the key word and, meaning I need them to be male and blonde at the same time. Is that possible? Well, yes, we have 5 males that are blonde, 5 out of 50. So that reduces to 1 out of 10. Now finally, we're going to use the addition rule because we have these words or in the middle. The first example here with or is the probability of female or brown. So we can really have either this characteristic or that. So first, the probability of females. Well, there are 30 out of 50. This is the first part of the addition rule, the probability of A. I just did that part. Plus the probability of B, which is brown hair. And it looks like there are 14 out of 50 that have brown hair. That's part B of the formula. But is it possible to be female and have brown hair at the same time? Yes. This is very different from last time. Female and brown hair is not mutually exclusive. In fact, we have 6 females that have brown hair. So we have to take away those 6 because essentially when we added these up in the table, the 14 and the 30, we added that 6 twice. Remember the 14 had that 6 in it going down the column, and then the 30 had it in that row. So we counted this 6 twice. That's why I circled it. So we have to subtract it off. So 30 plus 14 is 44. Minus 6 is 38. That's a really sloppy 38. Let me try that again. 38 out of 50. And I don't have room to reduce it, but it would reduce. Last example. So let's say we want to do the probability of selecting a male or having other hair color. A male or other hair color. Well, the males, that's simple. There's in this row there are 20 males out of 50. And what's the chance that I get other hair color? Well, that's also 20 out of 50. But notice we counted the 7 twice. That's the probability of being male and having the other hair color at the same time. That's possible. So we subtract the 7 out of 50 and we do our math here. 20 plus 20 is 40, minus 7 is 33 out of 50, which does not reduce. And that's our final answer. So you got to be ready to be able to do probabilities from tables using the addition rule for disjoint and, mutually exclusive events and not mutually exclusive events. So good luck, and we'll see you on 5.3.